Hello. So today I want to discuss about a problem that appeared in CMI entrance exam 2021. It's mainly on elementary number theory based on prime numbers. So the question is, I have a prime number p. I have to determine whether the number p square minus p is always divisible by 3 or not. Whether among the numbers p minus 1 and p plus 1 exactly one of them is divisible by 6 or not. Whether p square minus 1 is always divisible by 24 or not, and whether among the numbers p plus 1, p plus 3 and p plus 5 exactly one of them is divisible by 8 or not. This will give you a general idea to how to deal this type of prime number problems. So let's get started.
This video is sponsored by Chinta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
For the first part, what are the distinct remainders when I divide a number by 3? The distinct remainders either 1 or 2 or 0, right? 0, 1, 2 are the distinct remainders you can get when I divide an integer by 3. So p is either congruent to 0 mod 3 or 1 mod 3 or 2 mod 3. These are all possible cases. Whether p is a prime or not, it doesn't matter. This means what? P square minus p is congruent to 0 square minus 0, that is 0 mod 3, and it's fine. P is congruent to 1 mod 3 implies p square minus p is 1 square minus 1, that is 0 mod 3. This is again divisible by 3, okay. P congruent to 2 mod 3 means what? P square minus p is congruent to 2 square minus 2, like it is congruent to 2 mod 3. Like 2 square is congruent to 4 minus 2, and that is a problem. So p congruent to 2 mod 3, this implies p square minus p, it is not congruent to 0 mod 3. For like if p is of the form 3k plus 2, then I have a problem for the first part. So let's take an prime of the form 3k plus 2. Say example p equal to 5. So in that case p square minus p is 5 square minus 5, that is 25 minus 5, 20, and it is not divisible by 3. It gives remainder 2. So the first part, it is false. What about the second part? Okay, in this part I have to divide p by 6. So what are the remainders if I divide p by 6? Remainders are all possible. Remainders are 0, 1, 2, 3, 4, 5. So p is either of the form 6k plus 1, 6k plus 2, 6k plus 3, 6k plus 4 and 6k plus 5. Now can all of them occur? See, if p is of the form 6k plus 2, that would imply p is even. But there is no even prime. We assume that p greater than equal to p greater than 3. But there is no even prime greater than 3, like only even prime is 2. So this is not possible. Similarly, in this case, if p is 6k plus 3, then in that case 3 divides p. That would imply p equal to 3, because 3 divides a prime number, so that number must be 3. But here we are given that p greater than 3. So this is also not possible. Similarly, by even contradiction, that would imply also p equal to even. 6k plus 4 is also not possible. So this is a good lemma. What we get is that any prime p greater than 3 is of the form 6k plus minus 1. Like it is either congruent to 1 or congruent to minus 1 modulo 6. So in this question, if my p is congruent to 1 modulo 6, then p minus 1 is divisible by 6 and p plus 1 is not divisible by 6. Because p is congruent to 1, so p plus 1 gives remainder 2 when divided by 6, and And if it is not the case, then p is congruent to -1 modulo 6. In that case, p minus 1 gives remainder -2. It means it gives remainder 4 when divided by 6, and p plus 1 is divisible by 6. So this statement is true. True. Now what about the third part? This is an important lemma. Any perfect square is either congruent to 0 or it is congruent to 1 modulo 3. And you can easily check it by checking, like if n is congruent to 0, that would imply n square congruent to 0. N is congruent to 1 modulo 3 implies n square is congruent to also 1. N is congruent to 2 implies n square is congruent to 2 square. I mean 4 and 4 is equivalent to 3. 4 is equivalent to 1 modulo 3. And 4 is congruent to 1 mod 3. So in either cases, the remainders of n square either 0 and 1. So using this, and we have to see, to have p square minus 1 is divisible by 24, we individually need that 3 divides p square minus 1 and 8 divides p square minus 1. So as p is a prime, p square minus 1 is divisible by 3. As p is greater than 3, 3 doesn't divide p, as p is a prime, so p square is not 0, so p square is congruent to 1 mod 3. And this part is done. I need to show that, now we have to show that 8 divides p square minus 1, and we can prove it easily that any, this is also an important lemma, you will encounter them frequently in number theory, solving the differential equations and related stuffs, that any odd perfect square, any odd square, for any odd perfect square n square is congruent to 1 modulo 8. Like any odd perfect square gives remainder 1 when divided by 8. We can check this easily, again using the same way. If n is congruent to 1, see, any odd number cannot leave an even remainder when divided by 8. So all possible remainders are 1, 3, 5 and 7. No, nothing else is possible. In this case, what about n square? N square is 1 square, n square is, here it is 3 square modulo 8, here it is 5 square modulo 8, here it is 7 square modulo 8. And 1 square is 1. 9 is again congruent to 1 modulo 8, 25 is congruent to 1 modulo 8, 49 is also congruent to 1 modulo 8. So in all cases we get n square is congruent to 1 modulo 8. So n square minus 1 is always divisible by 8. So this is true. So what we get, that 3 divides p square minus 1 and 8 divides p square minus 1, and 3 and 8 are co-prime. So p square minus 1 is divisible by 3 into 8 also, because those part 3 that divides, those cancel p square minus 1. Those parts cannot be cancelled by 8 because 3 and 8 has no common factors. So if we cancel out 3 with p square minus 1, in the numerator whatever we have left, 8 cancels that part, not any other part. So we have, this is a very common lemma, that we have a number a divides n and b divides n. If GCD of ab is 1, then ab divides n also, because they doesn't take out any common part. Sorry, ab divides n, so we don't have any deficiency in common parts. So 24 divides p square minus 1. So this is true. This is also true. We need to see whether p plus 1, p plus 2 and p plus 5, among them some of them are divisible by 8 or not. So we will do this by again checking cases. P plus 1, p plus 3 and p plus 5. If p is congruent to 1 mod 8, then what is about p plus 1, p plus 2 and p plus 5? P plus 1, p plus 3, comma p plus 5, they are congruent to 2, 5 and 7. Wait, p is congruent to 1, so 1 plus 1 2, 1 plus 3 4 and 1 plus 5 6 modulo 8. So none of them is divisible by 8 because both leave remainders 2, 4 and 6. P congruent to 3 implies this is congruent to 3 plus 1 4, 3 plus 3 6, 3 plus 5 8. So if P is congruent to 3 modulo 8, then P plus 5 is divisible by 8. P is congruent to 5 implies 5 plus 1 6, 5 plus 3 8 and 5 plus 5 10, and 10 is congruent to 2. And P is congruent to 7 implies this is congruent to 7 plus 1 8, 7 plus 3 10 means 2, 7 plus 5 12 means 4. So in these 3 cases we get one of them is divisible by 8 because we have 0 remainder in either cases. But the first case gives me a problem. Like when is P congruent to 1 mod 8, we get that none of the numbers P plus 1, P plus 3 and P plus 5 is divisible by 8. So if P is of the form 8k plus 1, we have a problem. Like say get any 8k plus 1 prime. So like keep putting on values until you get a prime. Like k equal to 1, it is 9 not prime, but k equal to 2 means P is 17. It is a prime of the form 8k plus 1, and you can see 17 plus 1 18, P plus 1, P plus 3, P plus 5 is 18, 20, 22. None of them is divisible by 8. So this statement is false. So only B and C are true. And we are done. This ends the problem here.
Chinta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Chinta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Chinta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit chinta.com.